Okay, let us continue the third part of today's class. Okay, because translation is, by definition of topological vector space, continuous, all translations are homeomorphisms. Okay, we will introduce what are homeomorphisms later. So every base for the neighborhoods of the origin can be translated to a base for the neighborhoods of any given vector. Okay. So next, let us go to problem 14. What is a subfield? Okay, why do we need to know what is a subfield? Okay, because let us see. Okay, because it appears in the solution to problem 13. What is a locally convex space? Okay, let us see the solution. Okay, a subfield E of a field F. Okay, we will introduce what is a field later. Okay, a field F is a subset of F that is a field with respect to the field operations of F. Equivalently, E is a subset of F that contains 1 and is closed under addition, multiplication, additive inverse, and multiplicative inverse of a non-zero element. This means that 1 is in E. Okay, why the number 1 must be in E? Okay, I will explain it later. That for all A, B in E, both A plus B and A dot B are in E. Okay, because the subfield is closed under addition. So for all A, B in E, okay, A plus B must also in E. Okay, and the subfield is also closed under multiplication. So A dot B must also in E. And that for all A is not equal to 0 in E, both negative A and 1 over A are in E. Okay, this is because negative A is the additive inverse of A, okay, non-zero A, and 1 over A is the multiplicative inverse of the non-zero A. Okay, and because A and 1 over A are both in E, so A dot 1 over A, which is equal to 1, must also be in E. Okay, because the subfield is closed under multiplication. Okay, next, problem 15. What is a field? Okay, why do we need to know what is a field? Okay, because field, this term appears in the solution to problem 14. Excuse me. Okay, solution. Formally, a field is a set F together with two binary operations on F called addition and multiplication. What is a binary operation? Okay, let me explain it. A binary operation on F is a mapping from F times F to F. Okay, what does this times mean? Okay, what does a field times itself mean? Okay, you can see that a field is a set. Okay, so this times operation is between two sets. Okay, we will explain the meaning of this red times later. Okay, that is a correspondence that associates with each ordered pair of elements of F a uniquely determined element of F. The result of the addition of A and B is called the sum of A and B and is denoted A plus B. Okay, I think it is very intuitive for you. Okay, similarly, the result of the multiplication of A and B is called the product of A and B and is denoted AB or A dot B. Okay, these operations are required to satisfy the following properties, referred to as field axioms. Okay, in these axioms, A, B, and C are arbitrary elements of the field F. Okay, so the followings are 6 field axioms. Okay, the first one is called the associativity of addition and multiplication. Okay, it says that if you want to compute A plus B plus C, okay, then you can compute B plus C first, and then compute A plus parentheses B plus C. Okay, or you can also compute A plus B first, then compute A plus B parentheses plus C. Okay, the two equations are equal to each other. Okay, similarly, if you want to compute A dot B dot C, okay, then you can compute B dot C first and compute A dot, okay, B dot C. Or you can also compute A dot B first, then compute A dot B, okay, dot C. Okay, again, the result of two equations sorry. Okay, are equal to each other. Okay, the second field axiom is commutativity of addition and multiplication. Okay, it says that A plus B is equal to B plus A and A dot B is equal to B dot A. Okay, the third field axiom is the additive and multiplicative identity. Okay, it says that there exist two different elements, 0 and 1 in F, such that A plus 0 is equal to A and A dot 1 is equal to A. Okay, the fourth field axiom is additive inverses. Okay, it says that for every A in F, there exists an element in F denoted negative A called the additive inverse of A, such that A plus negative A is equal to 0. Okay, the fifth field axiom is multiplicative inverses. Okay, it says that for every a is not equal to 0 in F, there exists an element in F denoted by a to the power of -1 or 1 over a, called the multiplicative inverse of a, such that a dot a to the power of -1 is equal to 1. Okay, the sixth field axiom is distributivity of multiplication over addition. Okay, it says that a dot parenthesis b plus c is equal to parenthesis a dot b plus the parenthesis a dot c. Okay, please note that I did not say the priority of the multiplication is higher than the priority of the addition. So we need to use parentheses and parentheses here. Okay, examples. First, rational numbers Q form a field. Okay, you can check rational numbers Q for the above 6 field axioms, and they will all be satisfied. Okay. Second, the real numbers R with the usual operations of addition and multiplication also form a field. Okay, third, the complex numbers C also form a field. Okay, so this is all about the field, the definition of a field. Okay, so next let us look at problem 16. What is the meaning of the red times in the solution to problem 15? Okay, let us see the first time. Okay, here the red times appear. Okay, here. Excuse me. Okay. Solution in mathematics, specifically set theory, the Cartesian product of two sets A and B, denoted A times B, is the set of all ordered pairs small a and small b, where small a is in capital A and small b is in capital B. In terms of set builder notation, that is, okay, capital A times capital B is equal to this set. Okay, this set contains the ordered pairs small a and small b. Okay, given that small a is in capital A and small b is in capital B. Okay, a table can be created by taking the Cartesian product of a set of rows and a set of columns. If the Cartesian product rows times columns is taken, the cells of the table contain ordered pairs of the form row value and column value. Okay, please see figure 20. Okay, figure 20 shows the Cartesian product A times B of the sets A with elements x, y, z, and B with elements 1, 2, 3. Okay, let us see this figure. Okay, I need to zoom in this figure. Okay, good. Set A contains 3 elements x, y, and z. And set B also contains 3 elements, 1, 2, and 3. Then A times B contains 9 elements, okay, which are ordered pairs. So first is x1 and x2 and x3. Okay, it is the first row. And the second row contains y1, y2, and y3. Okay, and finally the third row contains z1, okay, z2, and z3. Okay, let us go back to the, okay, here. Okay, problem 17, what does field is ordered mean? Okay, why do we need to know what does field is ordered mean? Okay, because it appears, okay, let us search for it. Okay, here, when we explain what is a cone, okay, the field is ordered appeared here. Okay, so let us see what does field is ordered mean. Okay, solution. In mathematics, an ordered field is a field together with a total ordering. Okay, we will explain. I will explain what is a total ordering in the next problem. Of its elements that is compatible with the field operations. The basic example of an ordered field is the field of real numbers. Okay. So problem 18, what is a total ordering? Okay, solution. In mathematics, a total or linear order is a partial order. Excuse me. Okay, so what is a partial order? We will explain it in the next problem, in which any two elements are comparable. That is, a total order is a binary relation, smaller than or equal to, on some set X, which satisfies the following for all A, B, and C in X. Okay, first, A is smaller than or equal to A. This is called reflexive. Second, if A is smaller than or equal to B, and B is smaller than or equal to C, then A is smaller than or equal to C. This is called transitive. Okay, third, if A is smaller than or equal to B and B is smaller than or equal to A, then A is equal to B. This is called antisymmetric. Okay. 4. A is smaller than or equal to B, or B is smaller than or equal to A. This is called strongly connected, formally called total. Okay, what does this mean? Okay, this means that this equation and this equation, okay, there are two equations here. Okay, at least one of these two equations is true, okay, or will establish. Okay, total orders are sometimes also called simple, connects, or full orders. Okay, a set equipped with a total order is a totally ordered set. The terms simply ordered set linearly ordered set. Excuse me. And those sets are also used. The term chain is sometimes defined as a synonym of totally ordered. Okay, set but refers generally to some sort of totally ordered subsets of a given partially ordered set. Okay, an extension of a given partial order to a total order is called a linear extension of that partial order. Okay, let me give an example. Okay, let X be the set of all real numbers and the binary relation smaller than or equal to. Okay, then it is a total order. Okay, for example, okay, 1, 2, and 3 is in is in R. So 1 is smaller than or equal to 1. Actually, 1 is equal to 1. Okay, and if 1 is smaller than or equal to 2, and 2 is smaller than or equal to 3, then 1 is smaller than or equal to 3. Okay, so this is also correct. Okay, 3. If A is small, if 1 is smaller than or equal to 1, and 1 is smaller than or equal to 1. Okay, here I set A be equal to 1 and B is also equal to 1. Then 1 is equal to 1. Okay, it is very easy. Okay, so this is also correct. Okay, so 4. 1 is smaller than or equal to 2, or 2 is smaller than or equal to 1. Okay, so we can see that only 1 is smaller than or equal to 2 is true, and 2 is smaller than or equal to 1 is false. Okay, so here we use the word or here. Okay, so this is also correct. Okay, so we know that an example, or we say an easiest example for a total order is the smaller than or equal to on the real set of all real numbers. Okay, next, let us see the next problem. Problem 19. What is a partial order? Okay, solution. A partial order relation is a homogeneous relation. Okay, I will explain what is a homogeneous relation later. That is transitive and antisymmetric. Okay, I will explain what is transitive and antisymmetric later. Okay, however, you can refer to the solution in the last equation. Okay, here is the transitive and here is the antisymmetric. Okay, so let us go back to here. Okay, there are two common subdefinitions for a partial order relation for reflexive and irreflexive partial order relations. Okay, also called non-strict and strict respectively. The two definitions can be put into a one-to-one correspondence. Okay, I will explain what is a one-to-one correspondence later. So for every strict partial order, there is a unique corresponding non-strict partial order and vice versa. Okay, the term, okay, it is 25 minutes. See you next time. Good.